So in this second video, I'm going to look at the three stages of a lift that's starting at a ground floor and working its way up to a top floor. Now, obviously, we set this system up in the first video, and I'm just going to show you the three motions of the lift. So obviously, motion one would be where the lift initially accelerates upwards until it reaches its speed that's set for this building. Then there is no acceleration as the lift continues at constant speed while the passengers are on their journey in the lift. Then finally, section 3 is where the lift decelerates until it reaches zero and its destination floor. And you'll notice that the acceleration arrows now are downwards. That's showing that the motor is decelerating the lift. Now, all I can do in these three situations is effectively apply F equals ma. We've got forces, masses and accelerations, and we tend to apply F equals ma in the direction of motion. So if I look in the first instance, applying F equals ma upwards in the direction of motion, we've got the tension and lift acting upwards, we've got the mg acting downwards, and that's equal to ma. So the tension and the lift is equal to mg plus ma. In our second situation, obviously the lift is still moving upwards, so we apply F equals ma. But in this case, the lift has accelerated. The motor is now working the lift at constant speed. It's not going any faster, not getting any slower. So when we apply F equals ma, we've got T minus mg again. But obviously, with A being 0, ma is 0. So here we've got the tension in the lift cable is equal to mg. Now, in the final situation, obviously the lift is still moving upwards, and we're going to apply F equals ma in that direction. So again, we have T minus mg is equal to, and in this case, obviously the acceleration is a deceleration, so it's acting in the opposite direction, is equal to minus ma. And when we rearrange this, we get T is equal to mg minus ma. Now, this is interesting. If we take the second situation first of all, when the lift is moving at constant speed, when there's no acceleration, that's almost the same as when the lift is stood still waiting to move. You're stood in the lift and you're not feeling anything because the lift isn't moving. And similarly, the same is when you're actually moving at constant speed. You're in the lift, but you don't actually realise the lift's actually moving. If we now look at the first situation, now when you get in a lift at the ground floor and the lift starts to initially accelerate, you feel that idea of weight being bearing down on you, and you feel the lift floor push up against you and you're pushing back down. And if you notice here, the tension in the lift cable is equal to the weight plus ma. In other words, there's that extra bit of force of pushing down as the lift pushes up, which makes you give that feeling of weight. Similarly, if we look at situation 3, when the lift is actually decelerating, you get that feeling of lightness as the lift suddenly starts to decelerate. And you can see there, the tension in the lift cable is actually reducing. And we have this mg minus ma effect, where you actually feel lighter for that instant as the lift suddenly starts to decelerate. And it's handy to remember these situations and relate it to real life, in that the first instance